in the previous lecture we talked about the balances of carrier density, momentum density and energy density, these parameters related to the carriers. We talked about the balances under equilibrium conditions. We explained what each balance means. Then we said that we disturb the equilibrium to create a directed motion. This directed motion we analyzed under two situations, namely quasi equilibrium and non equilibrium. So when the disturbance from equilibrium is small, we explained what are the balances in carrier, momentum and energy. Then when the disturbance is large, non equilibrium conditions, for that situation also we explained what are the balances in carrier, momentum and energy. How in terms of balances of these three quantities, which is analogous to talking about physical phenomena in terms of mass conservation, momentum conservation and energy conservation, how in terms of these we can explain the linear relation between velocity and driving force for small driving forces and saturation of the velocity for large driving forces. Then we introduced the concept of carrier temperature. So we said that the random thermal energy of carriers, the random energy of carriers even under applied voltage, which includes the thermal energy as well as the energy acquired from the electric field. So this random component, the random component of this energy, kinetic energy of carriers, can be associated with a temperature called the carrier temperature, in the same way as we associate lattice temperature with the random vibrational energy of lattice atoms, or we associate an ambient temperature with the energy density in the ambient. We also explained with an analogy how the balances between the energy of the carriers and energy of the phonons is achieved, how the energy exchange happens between them, how the energy of the carriers can be much different from energy of the phonons, or the temperature of the carriers can be very different from temperature of the phonons. Now we want to proceed from this point and explain some of the other phenomena such as velocity overshoot. So here is the repetition of some information related to carrier temperature from the earlier lecture, where we talk about the carriers, the phonons and the ambient, and the energy exchange between these entities. The energy input from the driving forces is directly into the carriers, so it is the carriers which derive the energy out of the forces, and then by energy exchange through scattering they pass on the energy to phonons, and which in turn pass on the energy through phenomena of conduction, convection or radiation to the ambient. Now let us talk about the result of balances for drift transport in terms of the carrier temperature. So here this means we will discuss about what happens to the carrier concentration n, the directed velocity Vd or drift velocity Vd, and carrier temperature. Under equilibrium, carrier balance results in the relation carrier concentration equal to n naught, equilibrium carrier concentration. Momentum balance leads to the conclusion that drift velocity is 0, and energy balance leads to the conclusion that the carrier temperature is equal to lattice temperature is equal to ambient temperature. Here energy input in this case is 0. Let us move to quasi equilibrium. In quasi equilibrium the carrier balance is the same, n equal to n naught, result is the same for carrier balance. For momentum balance you get a drift velocity which is approximately equal to force into the momentum relaxation time under equilibrium. So this is the momentum divided by the effective mass. So between two collisions, this is the drift velocity that a carrier acquires. The momentum relaxation time is approximately equal to that under equilibrium, under quasi equilibrium. This drift velocity, which is greater than 0, however, is much less than the thermal velocity. Now that is the meaning of quasi equilibrium, that the drift velocity is much less than thermal velocity, because we explained earlier that the saturation velocity is of the order of the thermal velocity. The force on the carrier is given by minus q times the electric field for drift transport. Now the energy balance, what the energy balance says is that the energy input is small from the driving force, this energy is small, the carrier temperature is approximately equal to lattice temperature. So this is the statement of quasi equilibrium, that the energy of the carriers and phonons is more or less same, the difference is not much, even though the carriers are getting energy from the driving force, because that energy gained is small. However, both these temperatures can be different from the ambient temperature. Okay, so these temperatures can be more. Now this is because suppose we consider a simple block and you apply a voltage here, a current flow is set up I, and this is voltage V. Now I into V is the power input into the sample. Now this power is going to be dissipated as heat. So when the semiconductor dissipates heat, its temperature can be different from the temperature of the ambient. Now inside we have separated the temperatures of the carrier and the lattice. Okay, so these two however can be same, but both of these can be different from TA because the resistor is dissipating energy, okay, heat. So one should not think that under equilibrium the ambient temperature also has to, in quasi equilibrium the ambient temperature has to be equal to the lattice temperature or carrier temperature, right? That need not be necessary. Now let us move to non-equilibrium. For the force conditions considered here, we do not have any impact ionization and so on, therefore the carrier balance leads to the conclusion that the carrier concentration is equal to equilibrium carrier concentration. The momentum balance leads you to the result that the drift velocity gets saturated at about thermal velocity. So you see in this equation the force is not there, this clearly indicates saturation, okay, with the applied force. The energy balance, it says that the energy input is large from the driving force, you are inputting a large amount of energy into the carriers. As a consequence, the carrier temperature is more than lattice temperature. You see this is the situation in non-equilibrium, and the lattice temperature is more than ambient temperature because the device or the semiconductor is dissipating heat. So now you have a net flow of energy from the carriers to the phonons or lattice and from the phonons to the ambient, because the temperatures of these three entities are different. So you see this is how the concept of carrier temperature allows you to express the results of energy balance in a very simple form, okay. Let us summarize the results of balances for drift transport in graphical form. So whatever we have discussed, let us put it in the form of a graph, because a graph expresses a lot of detail in a very compact form. So what you can say in many words, you can say succinctly in the form of graphs. Another advantage of using graphs to explain your understanding is because the graphs or diagrams remain longer in memory than words. So the result of carrier balance is n equal to n naught as a function of E. So E is the electric field that is driving the current in drift. Then let us discuss the energy balance. The result of energy balance is that electron energy, kinetic energy of electrons, it remains at Wn0 when the electric field is 0. So here the electric field is 0 at this point, it is Wn0. Now over a small region here it remains approximately at Wn0 because this is quasi equilibrium. So this dashed line, to the left of this dashed line we have dashed vertical line, blue vertical line, we have quasi equilibrium. So in quasi equilibrium Wn remains approximately equal to Wn0, and thereafter however as you enter non equilibrium region the Wn starts increasing rapidly with electric field. Now you can express the same result in terms of temperature. If you did that, then this is the electron temperature T suffix n. So we use T suffix c if you are talking of carrier in general to imply either electron or a hole, but if you are specifically referring to electrons then we will call it as T suffix n. If it is holes that we are referring to then we will call it T suffix p. So the electron temperature Tn remains approximately equal to the lattice temperature in equilibrium and quasi equilibrium, and thereafter it increases. The momentum relaxation time, which is a function of carrier temperature or kinetic energy of carriers, it changes as shown. So as the energy of the carriers increases or carrier temperature increases, the momentum relaxation time falls. However in quasi equilibrium it remains approximately equal to the equilibrium value, and the fall in momentum relaxation time occurs in non equilibrium situation. In fact quantum mechanical analysis shows that for large electric fields in this region the momentum relaxation time is inversely proportional to the electric field, and that is why the product of the electric field and momentum relaxation time becomes a constant, and that is what results in velocity saturation. So here is the velocity which is the result of momentum balance. So it increases linearly in quasi equilibrium and then tends to saturate. So this is how from carrier balance, energy balance and momentum balance we derive the velocity field curve for drift transport. We will do similar exercise for velocity overshoot curves also. Now this straight line here region has a relation drift velocity is given by minus q times tau m0 by mn into the electric field. The negative sign is because for electrons the velocity is in the direction opposite to that of field, that is why here we have plotted modulus of Vd, so that you can show things in the positive axis. Now this quantity q times tau m0 by mn is referred to as mobility, about which we will discuss later. Let us move to velocity overshoot. Now you will recall that we discussed two types of velocity overshoot, or in fact three types. Okay. So in one form of velocity overshoot, the velocity overshoot results from a sudden step in the electric field as a function of time. The second form of velocity overshoot results from a sudden step in electric field at particular location in the sample, but under steady state conditions. Now these are the two forms of overshoot that we are going to explain. There is a third form of velocity overshoot, that is in the velocity versus electric field curve. For gallium arsenide you have velocity overshoot and a negative resistance region. Now that part we will not discuss in much detail. In fact, I will leave it as an assignment to you to arrive at some simple explanation for this phenomenon. So right now let us concentrate on the temporal velocity overshoot, which is a result of a temporal step in electric field. Temporal step means a step as a function of time. So this is the result that we have reproduced from earlier slide. So the electric field changes suddenly at this instant of time, and we assume that the step is sufficiently large. So the order of magnitude here is 10 volts per micron, and this is the velocity curve as a function of time, and this is what we want to explain, why it goes up then comes down and saturates. The order of magnitude of the velocities are shown here. They are of the order of thermal velocity at room temperature. Also note the duration of the transient here. So you can see it is about 0.3 picoseconds. Okay. Before going on to explain this velocity overshoot, let us draw a diagram of the structure and the biasing arrangement in which this is observed. So in fact it is similar to this. So this is a semiconductor. We will assume it is a uniform semiconductor. Further, let us assume it is n type, and between these 2 points suddenly we are applying a step in the voltage. So this is V as a function of time. Okay. This voltage step is large. This is a conceptual situation. Okay. When you apply such a large voltage, a large current can be there, and so you have to cool the sample and so on. So this experimental setup we are not discussing here. So we apply a sudden step in the voltage, as a result there is a sudden step in the electric field. Now the electric field is uniform throughout the sample, please understand this. So E uniform with X, so it is varying with T because the voltage step is varying with T, but always from this end to that end the electric field is uniform. Okay. So that is the situation, and what we are monitoring is this current which will follow the drift velocity characteristics. Now returning to the slide, so this is your electric field step inside the sample, and here we show the carrier energy as a function of time, which is a consequence of energy balance. Now we need to explain an important point here. Why do we start with energy balance? Now you know that we have to use energy balance, momentum balance and carrier balance, all the three, to explain any of these phenomena. The important point is that we must start with that balance consideration where the time constant associated with the relaxation is highest. So whichever process is slowest, we have to start with that balance consideration. For example, you know that carrier balance. So if there are excess carriers and they have to relax, then the time constant associated with relaxation of excess carriers is minority carrier lifetime. Time constant associated with relaxation of momentum in momentum balance considerations is momentum relaxation time, whereas the time constant associated with energy relaxation in energy balance is energy relaxation time. So if you look at these three time constants, namely the minority carrier lifetime, the momentum relaxation time and the energy relaxation time, then we know that the order of magnitudes of these quantities are as follows. The minority carrier lifetime is the largest, then comes the energy relaxation time, and then the momentum relaxation time. So what is the meaning of this? The excess carriers relax at the slowest rate. The energy relaxation is faster than relaxation of excess carriers, and momentum relaxation is the fastest. So if all these three processes are present, then the carrier balance equation is the one that one must start with. Okay. Now in our present case, the carrier concentration is constant with time, so there is no question of carrier relaxation. Therefore, in our present situation, we are left with the energy relaxation and momentum relaxation, and energy relaxation time is more than momentum relaxation time. So energy relaxes much more slower than momentum. So whichever is the slowest process of relaxation, we must start with that, because the faster processes can adjust with the slow process. Okay. So generally the behavior of the slowest process will be simple. So we start with that, and other processes which are faster adjust with the slowest process. So in this case, since carrier balance considerations are not important, because the carrier concentration is constant with time and it is equal to the equilibrium value, we start with the energy balance consideration. Okay. Now, so energy changes from Wn0 under equilibrium to the saturation value in the order of energy relaxation time. Now please note here we are only considering the order of magnitude of the quantities. If you are going to be if you want to be very precise, maybe it will be 2 or 3 times energy relaxation time. Okay, that will be the duration of this transient. So right now we will only be concerned about the order of magnitudes. When we talk about the equations, introduce the equations, then we will make this duration more precise. So the energy is increasing and then saturating. Consequently, see what is happening to the momentum relaxation time. The momentum relaxation time is decreasing from the equilibrium value tau m0 to a value tau m infinity, because as we have discussed earlier, the momentum relaxation time is a function of carrier energy, and higher the carrier energy, lower is the momentum relaxation time, because the scattering rate is more at higher energy. It is this variation of the momentum relaxation time that is crucial to explanation of the velocity overshoot. So as we will see, the fact that momentum relaxation time is very different from the energy relaxation time, it is much shorter than the energy relaxation time. This will be important for us to explain the velocity overshoot. Now let us see what is the consequence of variation of the momentum relaxation time. So here is the velocity curve, which is a consequence of the momentum relaxation time. Now for first view, this curve and this diagram looks a little complex. There are many things shown here. So let us develop this curve on the blackboard. So let us say the electric field is stepped at this instant. This is as a function of t, and the momentum relaxation time changes like this. Now it will remain equal to this value tau m0 for some duration until the energy really starts increasing, and that is where it starts falling. So let us say it falls like this, and this duration is of the order of the energy relaxation time, and this value is tau m infinity. Okay. Now we want to develop, so this is tau m, we want to develop the drift velocity versus time curve. Let us refer to the drift velocity versus field curve for steady state conditions. So you will recall the velocity field curve was something like this. Okay, this is under steady state evidently. So you will get this curve if you are increasing E very slowly and allowing the device to reach steady state for each condition. Now this is the magnitude of our electric field step. Now let us see under steady state conditions what would be the velocity for this electric field. So if I show this value as E1 and mark off this value here, let us say the E1 is coming somewhere here, say this is E1. So corresponding to E1, this is your velocity. So this is the so called saturation velocity. So under steady state conditions, after the transients have relaxed, you must achieve Vsat. So let us mark out the Vsat here. So let us say this is your Vsat. Now why does the velocity saturate? Because corresponding to this E1, your momentum relaxation time is tau m infinity, that is the momentum relaxation time marked here, and this momentum relaxation time depends on the electric field. So the velocity saturates because the momentum relaxation time in this region decreases inversely as the electric field. So product of this and the electric field becomes a constant. Now so the momentum relaxation time corresponding to this value is tau m infinity. So we could say that if your momentum relaxation time was tau m infinity for the whole duration, assume that immediately the system achieved momentum relaxation time of tau m infinity after you stepped it up, then your curve for velocity would be something like this. So in this time, which is tau m infinity, it will achieve velocity saturation. So this value, this is what would have been your curve. However, we find that at least during the initial stage of the transient, your momentum relaxation time is tau m 0 and not tau m infinity. Let us say in this duration. Now tau m 0 corresponds to the momentum relaxation time in the field was really low here. So on this curve it is in this region. Okay, so if your momentum relaxation time corresponds to the value here and your curve was increasing along with the electric field, so for the same electric field, if the momentum relaxation time was tau m 0, then you will achieve a velocity as shown here. You extend this straight line and this is your velocity that you will reach if your momentum relaxation time remained at tau m 0, which corresponds to the low electric field. Okay, so here your momentum relaxation time is tau m 0. So let us draw the curve for this extreme. So for this extreme your curve would be, so the curve would rise with time in the same way because the field is same, the acceleration is same, so it will rise, but it will do so now for tau m 0, and then you will get this saturation velocity. Now based on this we can predict what will be the velocity field, velocity versus time curve if your momentum relaxation time varies. So evidently your curve should start on this particular velocity time curve should start on this curve and end on this curve. It should end on this curve after the duration of the transient, that is energy relaxation time. So the curve would look something like this. So it will go up, and so it starts on this curve, but then gradually moves to the other curve because the momentum relaxation time changes. Now you can say, why can't I start on this curve and then end on the other curve right here? Why should I overshoot? Now the reason for this, and this is an important point, is that the momentum relaxation time changes from tau m 0 to tau m infinity rather slowly over the energy relaxation time interval. If the change from tau m 0 to tau m infinity was very rapid, if this energy relaxation time was very small, of the same order as these times, then the change of the curve from this curve to this curve would be very rapid, and in fact you will not get any velocity overshoot. So the velocity overshoot is happening, the curve is climbing on this particular curve corresponding to tau m 0, and this is corresponding to tau m infinity, because the system is not relaxing fast, it is taking time to relax, therefore it climbs up much higher here before it starts to move down, the velocity starts to move down. Okay, so that is the reason. Now here we have drawn curves for tau m infinity and tau m 0 to be having the same slope here, whereas here these corners would get rounded off in practice. So on the slide a realistic curve is shown where these corners have been rounded off. So let us look at this curve here. So you have seen these corners are rounded off. Now I want to emphasize that when we say when we put the term tau m 0 here, you should not think that this axis is tau m 0. Okay, so this axis is velocity. What we are saying is this velocity time curve is assuming that the time constant remains same as tau m 0 throughout the transient. So it is somewhat like plotting MOSFET curves. So you plot drain current versus drain voltage for different gate source voltages. So gate source voltage is a parameter. Similarly here tau m 0 and tau m infinity are parameters. Finally, to complete the picture, let us show the carrier balance consequences. So carrier balance consequences is that your concentration remains constant at n naught as a function of time. Now in the same manner, let us explain the spatial velocity overshoot. So here are the relevant diagrams for the spatial velocity overshoot. So the field changes abruptly at some location to a high value, and as a consequence the drift velocity varies as shown in this figure. Let us draw a structure diagram to explain what is happening here. So this is your semiconductor in which the field is suddenly stepped at some location. Now this is a steady state situation. Please note that things are not changing with time, unlike in the previous case. This is important because under steady state the current in the device will remain constant with x, and I is the current entering the device. Though the current remains constant in the device, we will find the velocity is going to change with distance because of this step response, and evidently the only way current can remain constant is carrier concentration should also change in a compensating manner to the velocity change, so that the current remains constant. So that is why in this case both the velocity and the carrier concentration both will change with distance. So we are not bothered about how this electric field step can be brought about. There can be several ways of doing this. Just to make a short mention, you could probably put a delta doping here, okay, that can create a field step, some sort of a charge in a short location. Let us look at the velocity response. So we find that while the step occurs at 0.45 microns here, the velocity starts increasing at 0.3 microns itself, that is before the step. Now you should not confuse this with a non-causal behavior. So it is not as though things are, when we use the word before, it does not mean it is before in time, okay, it is distance. So it is not a non-causal situation or unphysical situation. So such a curve would not be physical if this axis were time, because that would imply the velocity is anticipating the change in electric field, which cannot happen in practice. However, when it is with distance, the velocity can change before the location of the step in the field, and we will explain how this happens. So anyway, the velocity reaches a peak value beyond the step and then saturates, falls down and saturates. Now look at the distance over which the change is happening. This is about 0.3 micron to 0.6 micron. So about 0.3 microns is the distance over which the change happens, and this 0.3 microns is distributed. Part of it is before the step location and part of it is after the step location. Now let us explain this velocity overshoot. Following the approach for transient velocity overshoot, we will start with the energy balance consideration. In this case, though carrier concentration will change with distance, since it is not changing with time, there is no question of considering carrier relaxation with time. So the slowest process in this case is energy relaxation. Momentum relaxation is faster process. So that is why we are starting with energy balance considerations. So here is the change in energy as a function of distance. From the equilibrium kinetic energy Wn0, the energy changes to a saturation, new saturation value, higher value, over a distance Le from the location of the change in the field step. Here the energy begins to rise before this location, the reasons for which will become clear later. Right now, as an approximation, let us say it starts rising beyond this step. Now let us understand a little bit about this distance over which the change happens. Now this distance can be approximated as the energy relaxation time over which the energy relaxation happens, multiplied by the average velocity, which can be obtained from this velocity distance graph. So we could say, for example, to an approximation, the average velocity is about 1 into 10 power 7. So this is 1. So this is the average. Some region the velocity is higher and some other region it is lower. So average is 1 in 10 power 7. So if you do a simple calculation, energy relaxation time is about 1 picosecond. The average drift velocity just now we saw was 10 power 7 centimeters per second over the transient duration. Multiply these two, you get Le is equal to Vd into tau e, that is equal to 10 power minus 5 centimeters. So this is the order, this is not the exact value, this is the order, or 0.1 microns. Now this is how we get the order of the distance. So here you can see, so 0.45 to 0.6 is about 0.15 micron. So that is the Le, okay. Now you have the transient even, not transient, I am sorry, the change even before this. So that is why the change occurs over a distance more than Le, it is starting from here. Okay. Now based on this energy change, we can plot the momentum relaxation time change. So momentum relaxation time changes from tau m0 to tau m infinity, as in the earlier case, except that now it is happening over a distance as the energy is changing over distance. Now exactly following similar arguments, we can develop the velocity versus distance curve. So you have two extreme cases shown here. If your momentum relaxation time was tau m infinity throughout this duration, then you will achieve the saturation velocity corresponding to the velocity field curve. So let us return to this same diagram, this velocity field curve. If the size of your step here, if this value is E1, then corresponding to E1 under steady state conditions you have this saturation velocity. On the other hand, supposing your momentum relaxation time was tau m 0 throughout, that is this initial value, the higher value, then you will saturate at a higher velocity here. So this is that higher velocity, because in this region the time is tau m 0, and if you follow this right up to the field E1, then you will reach here. So this would be a higher saturation velocity. So that is what is shown here. So this is the other extreme curve. Now it is important to note that we are talking about distances, and so you are to convert from time to distance. So just as we converted from energy relaxation time to LE by multiplying the energy relaxation time by average velocity, we can convert from the previous case of transient velocity overshoot from this time tau m 0 and tau m infinity to corresponding lengths by multiplying with the average velocity in this duration. So that is how you get the length of this transient. So in this case, for example, this transient occurs over a smaller length and this occurs over a larger length. Okay, so now following similar arguments, your velocity field curve should start on the tau m 0 curve, but ultimately saturate on the tau m infinity curve. Also this change from tau m 0 to tau m infinity occurs slowly, and therefore the curve, velocity curve, gets a lot of time to climb up along the first curve before it starts moving towards the second curve. So that is why you get a velocity overshoot. Now let us explain why the velocity should start increasing earlier than this location. Okay, that will also explain why the energy starts increasing before the location of the field step. Now for that we need to go to the carrier concentration versus x curve, which is shown here. So here you find that the carrier concentration also is changing before this step. Now let us explain why this happens. Then based on this we can build up the variations of the velocity and the carrier energy. So supposing I plot here the velocity versus distance. Suppose it is like this. Now since the current density J is equal to Q times the concentration times the velocity, if Vd is a function of x, then n also has to be a function of x. Why? Because J should be constant. So here we have said I should be constant with distance, it is a steady state consideration. I is nothing but area multiplied by J. Okay. So over the area of cross section of this semiconductor, we are assuming that the current is uniform over this area. So Nx Vdx. So if Vd is a function of x, n also is a function of x to compensate for this variation, so that J is independent of x, it is a constant with x. So if I try to sketch n for this, I will get something like this. So this is the distance LE. Now this distance over which this transient occurs is really very short. So this variation of the carrier concentration is very rapid, causing large diffusion currents. You know, mobile carrier concentration, if it changes with distance rapidly, it will cause large diffusion currents. So really it is not possible for the carrier concentration to abruptly start changing beyond this point, because that would mean a large diffusion current. Just before that you find that the slope is 0. Okay? So this is not possible. So what happens is, therefore this carrier concentration corner change becomes smoothened out, so that such large diffusion currents do not arise, and so this becomes something like this. So now you see that is the reason why before the step in the field here, if I plot the field step, it will look like this. Before the step in the field, your carrier concentration has started changing, so that this variation is gradual to keep the diffusion current under control, not become too high. Now again, by the same rule, wherever n is changing with x, Vd also has to change with x. So really the Vd should start changing with x earlier, because n has started changing earlier. So this gets smoothened out here like this. And similarly, because of this reason, the kinetic energy curve also gets smoothened out, and it starts changing before the location of the field step. So this explains the complete velocity versus distance curve. Now we need to explain a commonly used terminology related to velocity overshoot, the kind of velocity overshoot we have discussed. It is called a non-local phenomenon. Now why should it be called a non-local phenomenon? That is what we explain next. Now both forms of velocity overshoot are shown here, so as a function of time and as a function of distance. Now suppose the velocity versus time or distance curve was decided by the local value of the electric field. In other words, if it was decided based on this velocity field curve that we have drawn here, which corresponds to steady state, actually it is not correct, but supposing we used this curve to predict, then your velocity versus time or velocity versus distance curve would be an abrupt change. Okay, so in other words, as written in the slide, if Vdt or Vdx were determined slowly by the local electric field, that is E at that time instant or E at that location. So the word local means the value at that particular location in time or distance. That is, the curve follows the VDE relationship of the steady state uniform field conditions. So if the velocity were determined by the local electric field, local in time or distance, then you would get an abrupt change, whereas actual situation is this. So velocity curve does not follow the electric field at that point. So the actual non-local velocity profile, where Vdt or Vdx is not determined solely by local Et or local Ex. So this is why the curve 2 is referred to as non-local. Curve 1 would be referred to as local phenomenon, whereas curve 2, where the velocity, let us say at this instant, does not depend on the field at that instant, right? So then that is the reason why it is called non-local. Now here is a simple analogy to explain how the word non-local arises. Okay, something that is something which we are more familiar with. So the carrier concentration in a semiconductor under equilibrium, which is non-uniformly doped. So the majority carrier concentration is not equal to NDX Nx does not follow Ndx if Ndx varies rapidly with x. So here is an example. Supposing your Ndx varies slowly like this with x, so this is Ndx. Then your Nx will also follow almost the same, because your formula is n equal to Nd plus p, okay, and minority carrier constant is small, so n follows Nd or Nd plus. But suppose you had a situation like this, so same curve will also correspond to Nx here. There is a rapid change in Nd, so this is Ndx curve. Then your mobile carrier concentration Nx would change like this, so this is your Nx curve. So now you see at this point the Nx is not equal to Nd, so this curve is not following this curve, therefore we can say this is non-local phenomenon, right. So Nx is not following the local Ndx. So now let us look at a few assignment questions for you. Starting with the treatment of an electron as a particle, summarize all the approximations made to derive the drift diffusion charge transport model. So we have come to the end of this module and end of this lecture. So that is why this is an assignment which tries to trace all the approximations which we have made to arrive at the drift diffusion transport model. Another assignment is describe the qualitative physics underlying the drift velocity overshoot due to a step increase in the field with time in no more than 75 words. So transient velocity overshoot you try to capture in 75 words, okay, not more than that. So whenever you have to write or explain something within a few words, you really have to spend a lot of time in clarifying the understanding and making it perfect. In fact, I can give you a quote at this point. A famous scientist, Pascal, once said while writing a letter that I am writing a long letter since I do not have time to write a short one. So whenever you want to write things precisely and briefly, then you have to spend a lot of time in clarifying your understanding. So that is the goal of this assignment. Then if you were to limit yourself to the ideas discussed in this course so far, what would you attribute the velocity overshoot in the velocity field curve as, for example, in gallium arsenide 2? So the velocity overshoot in velocity field curve. Explain your answer. Do not reproduce the answer from any book. So assume that you know whatever we have done in the last 4 or 5 lectures, and that is all, you do not know anything more. Then what would be the reason that you come up with for this kind of drift velocity versus field curve for electrons? So this is a modification of this curve. Here there is a saturation, but for gallium arsenide it goes up and then comes down. Now let us summarize this lecture and the module. Some key points. So this module discussed qualitative modeling of semi-classical bulk transport. A qualitative model is an intuitive visualization of phenomena by logical reasoning without involving intricacies of equations. Then we made the important point about qualitative modeling, namely, for faithful representation of the reality, a model should include all the significant physical effects at the qualitative stage itself. This is more important than the intrinsic accuracy of the subsequent mathematical solution of model equations. Approximations begin at the earliest stages of model development. We discussed qualitative models for equilibrium conditions followed by charge transport in the bulk of a large semiconductor. Learning outcomes of this module. So we had said in the beginning of this module that by the end of this module you should be able to do a few things. So now you can check whether you are able to do these things. So this list tells you in more detail what are the important points that we covered. So at the end of this module, I hope that you are able to explain qualitatively the following in semiconductors: the reason for terming certain mechanisms of carrier transport or carrier motion as semi-classical. So we said that between two collisions or scattering events, the carrier can be treated using Newton's laws, but the scattering event itself has to be treated quantum mechanically, and we explained why. Also we said that when we use Newton's laws to model the motion between two collisions, the mass of the electron or hole is not the same as mass in vacuum. It is an effective mass which captures the effect of the periodic lattice potential, and this effective mass also has to be derived from quantum mechanics, because the potential variations which give rise to this effective mass occur very rapidly over lengths which are very small compared to de Broglie wavelength. So because effective mass and scattering have to be treated quantum mechanically, there is no fully classical treatment of carrier transport, and that is why carrier transport is called semi-classical. We discussed the concepts of scattering, effective mass and carrier temperature in detail. Then I hope that you are able to explain the phenomena of ohmic transport, velocity saturation, velocity overshoot and ballistic transport of carriers. And finally, you should be able to explain the series of approximations leading to the drift diffusion thermoelectric currents, starting from the concept of carriers as particles in random thermal motion. Now we point out that we have not considered the range of validity of the particle approximation and the conditions under which the particle approximation is valid. So this point we will discuss in detail in a later lecture. We have however mentioned that the semi-classical transport is valid when the device size is sufficiently large so that there are a large number of scattering events and there are a sufficiently large number of electrons and holes in the device.